We'll start with the process synchronization. So before going for this process synchronization, we'll see what is shared data, right? The data which will be shared among the two processes, two or more processes, we say that data is shared data. Like if the shared data is accessed by the two or more processes concurrently, that will result the data inconsistency. Like if one process is using the data shared data, if that process modifies that shared data, when the other process comes at the same time, if that process also tries to modify the same data, that time the data will become inconsistent. Okay, to maintaining the data consistency requires a mechanism to ensure that orderly execution of cooperating process. Okay, if two processes are accessing the same data in the shared region, okay, if both the processes are try to manipulate the data, the time data will become inconsistent. Okay, so in order to maintain the data consistency, we require a mechanism to ensure that orderly execution of a cooperating processes. What is cooperating processes? We have discussed in previous sessions. Cooperating process is one that can affect or be affected by the other process executing in the system. Cooperating process is a process that can affect other process, or the process can be affected by the other process executing in the system. That process we call it as cooperating processes. Here, in order to maintain the data consistency, it requires a mechanism to ensure that orderly execution of these cooperating processes. If both the processes are access the shared data at same time, okay, if concurrently two processes access the shared data, that both modifies the shared data, that time data will become inconsistent. Okay, data will be modified, and the modified data will be used by some other process. Again, that will be data will be modified by other process. Okay, so complete the shared data will become inconsistent. Okay, to maintain that data in consistent manner, we need to follow a orderly execution of these cooperating processes. Okay, if the two processes are wants to access the shared data, they should follow some order of execution. Okay, in this, while following that order of execution, the modification of data, whatever the, if process 1 first access the shared data, the process 2 should wait. Okay, after that process 2 can access the shared data. Okay, like that we need to follow some order of execution for cooperating processes. Okay, this will be explaining here by taking the example called consumer producer and consumer problem. Okay, which we have discussed in the previous sessions. Okay, suppose that we want to provide a solution to the consumer producer problem that fills all the buffers. Okay, what the producer consumer problem will do? Producer produces an item, places in a buffer. Okay, it is a circular buffer. Okay, producer produces an item, he will place it in the buffer, consumer will consume it from the buffer. Okay, and it should be in the synchronized manner only. Once producer produces the item and places into the buffer, then only consumer should consume the item. Okay, excuse me, after producing an item only consumer can consume the item. Okay, we can do so by having an integer count that keeps track of the number of full buffers. Okay, here we use the variable called count. Okay, that will be used to keep track the number of items in the buffer. Okay, count. When the producer produces an item, producer will increment the count by 1. Okay, and when the consumer consumes this item, it will decrement the count by 1. Okay, count will become count minus 1. Okay, when after consuming it, consumer will decrement the count value. Okay, so here we can do it by having a integer called count that keep track of number of items in the buffer. Okay, initially the count will be set to 0. Okay, before producing any item, the count will be 0. Okay, and it is incremented by the producer after the producer produces a new item and add it to the buffer. Okay, once the producer produces an item, that will be added to the buffer, then the count value need to be incremented. Okay, and this count value is decremented by the consumer after it consumes a item in the buffer. Okay, after consuming an item in the buffer, consumer will decrement the count value by 1. Okay, that is the producer consumer problem. Producer produces the item and places in the buffer, and producer increments the count by 1, and consumer consumes the item from the buffer and it decrements the count by 1. Okay, like this, if in synchronized manner, if two process will access the shared data, then we can we can achieve that data consistency. Okay, so now we'll see, if you don't follow this order, what will happen. Okay, excuse me. Okay, this is the code for producer. You can see here, while count is double equal to buffer dot size. Okay, assume that the buffer size is some 5. Okay, count is, initially the count value is 0 for producer. Before producing an item, the count is 0. Okay, the count is equal to buffer size or not, we are checking here in this while loop. Okay, buffer size is 5. This is my circular buffer. Okay, the circular queue. Okay, buffer is having, buffer size is 5. Assume it, buffer size is 5. Count is equal to 0 initially. Okay, count is equal to buffer size, then we need to wait in the while loop only. Okay, this while loop we have given the semicolon. That means if this condition is true, okay, control will be in this statement itself. Okay, that is infinite time will be just waiting it. Okay, producer should not produce an item, the count is equal to the buffer size. That means buffer is full, right? If count is equal to 5, the buffer size is equal to 5. That time producer cannot produce an item, and if you produce an item, he can't, there will be no space in to place in the buffer. Okay, so producer should not produce an item if count is equal to buffer size. Okay, so that's what here we have given the semicolon for this while loop. Okay, if count is equal to buffer size, do nothing. Okay, producer should just wait until consumer consumes an item from the buffer. Okay, and if the count is not equal to buffer size, control will come out of this while loop, and this part will be executed. Okay, so now the count is, initially the count is equal to 0. Buffer size we have assumed it as 5. Okay, 0 is not equal to buffer size, so this while loop is false. Control will come here and the item will be added to the buffer now. Okay, initially the in value is 0. Okay, in value will be used to keep track of the circular queue. Okay, the in value is buffer of in will be the first position in the queue. Okay, so that is 0th position, you just assume. Okay, if in is equal to 0, buffer of in place, we need to produce an item, that item should be added in the buffer. Okay, the first item, assume that we have produced it 10. Okay, 10 will be stored in the first position in the buffer. Okay, so now Here we have another statement, that is in equal to in plus 1 mod buffer size. This statement will be used for uh, to transfer the control from the fourth position to the zeroth position. Okay, it's a circular buffer, circular queue. Okay, to change the position from the fourth position to the position 0, we are using this statement. Okay, if in is equal to 4, 4 plus 1 mod buffer size is 5. Okay, 4 plus 1 is 5, mod buffer size is 5, we will get 0. Okay, to transfer the uh, value of in from 4 to 1, we are using this condition. Okay, this is to update the array. Okay, increment the array. Okay, if it is 4, array size is 4, array is fourth position, then if you want to because it is a circular queue, we are using it. So to change from the fourth position to 0 position, we are writing this condition. Okay, in equal to in plus 1 mod buffer size. If in equal to 4, next where the item should be produced, item should be placed, next produced item should be placed in the 0th position, right? In a circular queue, we have items will be 0, 1, 2, 3, 4. 4 positions will be there. Circular queue, and the queue size is of 5. Okay, if the queue size is of 5, we have how many positions? 0 to 4 positions, right? The item which is produced by the producer will be first placed in the 0th position. Okay, next second position, next item will be produced by the producer will be placed in the third position, next item will be produced by the producer will be placed in the fourth position, next item which is produced by the producer should be placed in which position? It is 0th position. Okay, to transfer from the fourth position to the 0th position, we are writing this statement, that is in equal to in plus 1 mod buffer size. If in equal to 4, 4 plus 1, it will become 5. 5 mod 5 is 0. Okay, so once fourth position is filled, we need to go to the 0th position to place the produced item. Okay, because here we are using circular queue. Okay, that we have discussed when we are discussed the producer consumer problem. Okay, and here producer, after producing an item, okay, first initially the position is in value is 0. Okay, in is 0, so buffer of 0's location, the first item produced by the producer will be stored. Okay, assume that the item first we have produced is 10, so 10 will be stored in the buffer of in, that is buffer of 0th position. Now in value we are incrementing by 1 position, that is in is initially 0, 0 plus 1 mod buffer size 5. Okay, 0 plus 1 is 1, 1 mod 5 is 1. So now in value will be changed to 1. Okay, now the in value is here at this statement, in value is 1 now. Now we are incrementing count, that is plus plus count. Count is incremented by 1. So control again, go back here and we'll check it whether the count is equal to buffer size. If the count is equal to buffer size, producer should not produce any item. Here the what is the count now? Count is 1. 1 is not equal to buffer size is 5. 1 is not equal to buffer size. So this condition is not not satisfied. So control comes here. Next item will be produced by the producer. That is second item. So second item, we assume that it is 20. So second item will be placed in buffer of in value is what? That is 1. Okay, in buffers position 1, the second item will be placed. Okay, that is 20. Okay, 20 we are placing in the buffer. Okay, next we are updating the in, that is in equal to in plus 1 mod buffer size. In is 1, 1 plus 1, it is 2. 2 mod buffer size is 5. 2 mod 5 will get 2. Okay, now the in value will become 2. Now we are incrementing the count. Count will be incremented by 1. Now the count will become 2. Okay, so now 2 is not equal to buffer size. This statement is false. Control will come here. Producer will produce an item, that is third item, that is 30 producer is produced. That third item we are placing in. What is the in value? In value is 2. That means third position of the buffer we are placing the item. That is position number is 2. Okay, buffer position started from 0, 1, 2. Now in the buffer position 3, we need to position 2, we need to place the item 30 here. Okay, 30 will be placed in the third position in the buffer. That is in value is 2. That is in value specifies the always array will start with 0. Okay, first initially 0th position we have added the item 10. Position 1 we have added item 2, that is 20, and position 2 we are adding the item 30. Okay, that is that will be the buffer's third value. Okay, so we are adding the item into the buffer, and we are updating now the in value. In equal to in plus 1 mod buffer size. Okay, in is what? In is 2. 2 plus 1, 3 mod buffer size. Now the in value is 3 mod 5, we will get 3 mod 5, we will get 3. So in is updated with 3, and plus plus count. So count also we are incrementing it by 1. Until this the count is equal to buffer size, the loop will be executed and producer will be produce an item and store in the buffer. Okay, once the count is become 5, okay, count is equal to buffer size, that producer will stop producing the item, and producer will wait until consumer consumes the item from the buffer. Okay, this is the producer code. Okay, now we'll see the consumer code. Here in consumer code we have we need to check when the consumer cannot consume an item if the buffer is empty. Okay, if there is no items in the buffer, consumer cannot consume any item from the buffer. Okay, so for that here we are writing a condition while count is equal to 0, do nothing. That when count is equal to 0, if the buffer is empty, if the queue is empty, the count value will be 0. If count is equal to 0, do nothing. Okay, that time the consumer need to wait until producer produces an item. If producer produces an item, then only the consumer can consume that item. Okay, so if count is equal to 0, the consumer should just wait, should not consume anything, because there will be nothing to consume. The queue will be empty queue. Count is equal to 0 means the queue will be empty queue. Okay, and now the buffer of item is equal to buffer of out. Okay, initially the out is equal to 0. Okay, so at 0th location buffer item will be consumed by the consumer. Okay, that is buffer of item is equal to buffer of out. Out is 0. 0th position of buffer item, whatever item is placed in 0th position of buffer, that we have placed 10. 10 will be consumed by the consumer. Okay, so the buffer item will be updated with buffer of out, that is 10. Okay, now the out will be updated. Out is equal to out plus 1 mod buffer size. Okay, out is initially 0. 0 plus 1 mod buffer size is 5. Okay, 1 mod 5 is 1. So now out will be updated to 1. Okay, that means the next iteration, the buffer will be pointed with next position. Okay, initially the item which is placed in the buffer of buffer's 0th position, that is consumed by the consumer. In next iteration, consumer will consume the item which is placed in the second position in the buffer. Okay, that is buffer of 1. Okay, so for that purpose we are updating the out equal to out plus 1 mod buffer size. And here in this consumer code we need to decrement the count. Okay, count will be decremented by 1. If you decrement the count by 1, So initially when we are executing the consumer code, count is equal to 5. Okay, so count will be reduced by 1 here. Next iteration, count is not equal to 0. That is 4 is not equal to 0. This condition is false. Control will come here, consumer will consume an item, and count will be decremented. Count will be decremented until count is equal to 0. Okay, if the count is equal to 0, that means there is no items in the queue to consume by the consumer. So consumer need to wait until producer produces an item. This is the consumer code. Okay, next we'll see here what will happen if two processes executes the uses the shared data in improper order. Okay, what will happen? Data inconsistency will occur. Okay, if two cooperating processes are executing in improper manner, there will be a problem called race condition will occur. Okay, where two processes are accessing the shared data in inconsistent manner. You can see here in this producer consumer problem, what actually happens in the register, the values will be stored in registers. Okay, here this count plus plus could be implemented in this manner here. That is, register 1, first initially the count value will be stored in the register. What is the count value here? Initially the count value is 5. That will be stored in the register. Now the register will be, next statement here we have register 1 is equal to register 1 plus 1. That we are incrementing the register. This is a count plus plus is producer statement. Okay, we are incrementing the register by 1. Register equal to register plus 1. Okay, so now the count equal to register 1. What is the value in the register 1? Initial value of count, just assume it as 5. Now here what is the value in register 1 now after incrementing? Initially count is having 5. 5 we are storing in register 1. Okay, in this statement, register equal to register plus 1. That is, register is having how much value? What is the value the register is having? Register is having 5. 5 plus 1 we are storing again in the register 1. Okay, now the count, register 1 is having 6. 6 will be stored in the count. Okay, that is count plus plus producers part. Next we'll come to the consumers part, that is count minus minus. Count minus minus can be implemented like this by using registers. That is, count will be initialized to register 2. Okay, what is the initial value of count? Count value we have assumed it. The initial value of count is 5. Okay, 5 we are storing in register 2. Okay, next statement here we have is register 2 is equal to register 2 minus 1. Okay, register 2 is what value it is having? 5. That is decremented by 1 and stored in the register 2. That is count minus minus we are doing here. Okay, that is register 2 is having 5. 5 is decremented by 1. That is 5 minus 1. That is 4 will be stored in the register 2. Next statement here we have here is count equal to register 2. Okay, register 2 value is what now? It is 4. 4 we are updating by count. And here the process 1 is update, producer is updating the count by how much? It is 6. And here the consumer is updating the count value by 4. What is the actual value of count here? If here the both producer and consumer both are accessing the shared data at a time. Okay, both are concurrently accessing the shared data. Here the shared data is what? Count. Variable count is the shared data, and accessing the producer is accessing the count, and producer is accessing the count and modifying the count, where the consumer also is accessing the count variable and modifying the count variable. Okay, you can see here the producer one thread will be executing this statement, another thread will be executing this statement, another thread will be executing this statement. Okay, here one thread will be executing this, other thread will be executing this, other thread will be executing this. Okay, see here you consider this execution is interleaved with count equal to 1, count equal to 5 initially. So thread 0 is executing this statement, that is register 1 equal to count. Okay, it is a producer executes the statement register 1 is equal to count. Count is what value initially, that is 5. So 5 we are placing in register 1. Okay, next thread 1 is executing this statement, that is register 1 equal to register 1 plus 1, that is producer execution. Okay, producer executes register 1 equal to register 1 plus 1. Okay, here the register 1 is having value 5. After execution of this statement, register 1 will become 5. So 5 plus 1, it is 6. 6 will be stored in the register 1. Okay, next thread 2 is executing consumer execution. Okay, at consumer, because it is executing in concurrent manner. Here consumer execution, register 2 is executing this statement register 2 equal to count. What is the initial value of count? 5. 5 will be storing in register 2. Okay, so after execution of this statement, the register 2 will hold value 5. Okay, next the thread 3 is running consumer execution statement, that is register 2 is equal to register 2 minus 1. So register 2 is having what? Initially it was register 2, after executing this statement register 2 has value 5. 5 minus 1, it is 4. 4 we are storing in register 2. Okay, after this the thread 4 is executing a producer code, that is count equal to register 1. Okay, here what is the value in register 1? Register 1 is holding the value 6. So that 6 we are assigning to count, that is done by thread 4. Okay, and thread 5 is executing the consumer code. Okay, that is count is equal to register 2. Register 2 is having, what is the value? Register 2 is having value 4. 4 now it is stored in count. Okay, so producer code is updating the count by 6 and consumer code is updating the code by 4. Okay, you can see here the this is incorrect statement, that is um, counter equal to 4. Count is equal to 4, indicating that 4 buffers are full. Okay, count equal to 4 means there are 4 buffers are full, but in fact 5 buffers are full here. Okay, here initially the count was 5, so producer is produced one item and placed in the buffer. That time here consumer consumed one item and the buffer is empty by one item. Okay, consumer produced here initially the buffer is having 5 items. Next the producer produced another item and placed in the buffer. The consumer consumed an item from the buffer. Okay, and consumer decremented the counter by 1. Okay, now actually what is the buffer size? The buffer is size is 5. What is the number of items in the buffer is 5, but here we have the count, it is showing that count is 6 shown by the producer code, count is 4 shown by the consumer code, but actual count is 5. Okay, initially count of the buffer is 5. Producer produced an item and consumer consumed an item. Now after producer produced an item, the count become 5. Consumer consumed an item, the count become 5 again. Okay, so the count should be 5. Total number of items in the buffer should be 5, but here it is showing the producer code is showing the count is 6, consumer code is showing the count is 4. Okay, so this causes the data inconsistency. Okay, and this situation we call it as race condition. Okay, A situation where several processes access and manipulate the same data concurrently, and the outcome of the execution depends on the particular order in which the data has taken place, is called race condition. Okay, it's a situation where several processes access and manipulate the same data concurrently. Okay, at a time, data, shared data will be accessed and manipulated by many processes. Okay, and the outcome of this execution depends on the particular order in which the access takes place. Okay, in which order the outcome will be depends here, in what order the processes, processes modified that shared data. Okay, so the outcome of that execution will be depends on order of execution of those shared data items. Okay, so that is called as, that situation is called as race condition. Okay, and to guard against this race condition, we need to ensure that only one process at a time can be manipulating the shared data. Okay, so if to overcome these situations which we have discussed using producer and consumer, we need to ensure that only one process at a time need to access the data and manipulate the data. Here the count variable in this producer consumer problem, both producer 1 also is accessed and manipulated, same time producer 2 also, consumer 2, consumer also accessed and manipulated the count variable. So that situation, we have, there is a race condition arised. Okay, so outcome has become completely fault. Actual size of actual items in the buffer is 5 items, but producer code is showing that items in the buffer is 6, consumer code is showing that items in the buffer is 4. Okay, so that such situation we call it as race condition. To overcome from this race condition, we need to ensure that only one process at a time can be manipulating the shared data. We require that process must be synchronized in some way. Okay, the processes are synchronized way, the processes are accessed, then we can overcome from this situation. So that problem we call it as critical section problem. We'll discuss in next session.